Section 7.2 is on estimating a population mean. And the point estimate we'll be using for estimating the population mean is x bar, which is an unbiased estimator for that population mean mu. For many populations, sample means tend to vary less than other measures of center, such as the median, for example. Thus, the sample mean is the best point estimate of the population mean. In order for us to build the confidence interval for estimating a population mean, we have two cases, the first being sigma, the population standard deviation, is not known. Typically, this is the most common case. It is typically if you are trying to estimate the population mean, you're not going to know the population standard deviation at all, but that's besides the point. Anyway, the requirement that we have in order to compute this confidence interval, the first one is that the sample is a simple random sample. The second one is that the population is normally distributed or the sample size is greater than 30. But as we know, this uses one of those t distributions, so this sample size greater than 30 requirement, this could be a bit robust as long as the population is not that far off from being normal. And we could have something like 15 to 30 as a sample size. But typically greater than 30, the higher it is, the better. As is always a good train of thought. The confidence interval itself takes the sample mean x bar and adds and subtracts the margin of error. And all three of these representations all mean the same thing. The margin of error E takes the t statistic, so I should say the t critical value, t sub alpha divided by 2 times the sample standard deviation s divided by the square root of n, with a degree of freedom of n minus 1. It uses the critical t value based on the student t distribution with n minus 1 degrees of freedom. The rounding that we have for this is, if we're using the original data set, we round to one more decimal place than the original data set. And if we are using summary statistics, we use the same number of decimal places as used for the sample mean. And as I was saying, with regards to that normality requirement, this confidence interval is robust against departures from normality. The distribution should be somewhat symmetric with one mode and no outliers. The sample size, again, should be greater than 30, but sample sizes of 15 to 30 are adequate for population distributions that are very close to a normal distribution and doesn't really deviate that much, and also with no outliers. It is extremely far from normal. If it's extremely far from normal, then the sample size would need to be greater than 30, so such as a skewed right or skewed left distribution. The student t distribution was discovered by William Gosset, born 1876, died 1937. While he was working at Guinness Brewery, he was researching a way to calculate these probabilities and whatnot involving small sample sizes, because typically the normal distribution should not be used with small sample sizes. He was trying to find a distribution that could be used with small sample sizes. And he published it underneath the pseudonym Student, since Guinness prohibited the publication of the research, since it would be technically considered a trade secret, since it was researched there with respect to the company. If a population has a normal distribution, then the distribution of t is equal to x bar minus mu divided by s divided by the square root of n, is a student t distribution for all sample sizes n. And so that takes the sample mean x bar minus the population mean mu divided by sample standard deviation S divided by the square root of the sample size n. The degree of freedom is for the critical value of t sub alpha divided by 2 requires a degree of freedom that's 1 less than the sample size. The student t distribution is symmetric, as we could see, that being this blue and red graphs on here, just like the normal distribution, which you could see in green on this graph. But it has more variability in this with small samples. As you can see, the smaller the number is, notice how the distribution isn't as high, and there's more variability here in the tails. For that matter, even with a sample size of 12, there was more variability in the tails than the standard normal, which again was green. But it still has a mean of t is equal to 0, and for small sample sizes, the student t distribution approximates the standard normal distribution for large sample sizes. So notice how close 12 gets. As we have higher sample sizes, this will become more and more and more approximately normal. The procedure for constructing a confidence interval: we first need to verify the sample is a simple random sample, and the population is normally distributed, or the sample size is greater than 30. So we need to look at the histogram. Or that normal probability plot. I shouldn't say or. Probability plot. We would typically look at both the histogram and the normal probability plot. Since if you're already graphing the histogram, graphing the normal probability plot isn't that far of a stretch. Since we do not know the population standard deviation sigma, we would use n-1 degrees of freedom to find the critical value of t sub alpha divided by 2. And we would evaluate the margin of error by taking that t sub alpha divided by 2 times the sample standard deviation s divided by the square root of n, the sample size, for that margin of error e. The confidence interval, again, will be x bar plus or minus the margin of error. And we would round to one additional decimal place value if an original data set, or the same number of decimal places if using summary statistics. So, for example, let us compute the critical t-value for a 95% confidence level given that the sample size has n is equal to 15. So because the sample size is 15, the degree of freedom is 1 minus that, so 14. Since we have a 95% confidence interval, alpha is 0.05, and alpha divided by 2 is 0.025. And we could draw, or at least attempt to draw as well as humanly possible, a t distribution here, mean here of 0. T would be about, for 95% would be over here-ish. We want to know what this number is, so the area right here is 0.025. Again, when using technology, we are referring to the area to the left of it as opposed to above it. So if above it is 0.025, we would do 1 minus 0.025 to find the area below it, which, when we do the subtraction, we get an area of 0.975. So, for the critical t value of t sub 0.025, we would do this calculation by taking the probability that we have a t value. Because of the way SAS does it, we're going to look at the area below it. That t value t is supposed to be equal to 0.975, which is what this area here below it is. And tossing that into SAS will give us a t-score of 2.145. based upon that sample size of 15. Listed here are the weights in hectograms, or Hg, of randomly selected goals at birth based on data from the National Center for Health Statistics. Here are the summary statistics. N is 15. The sample size, X bar, the sample mean is 30.9 hectograms, and the sample standard deviation S is 2.9 hectograms. We want to use the sample data to construct a 95% confidence interval for the mean birth weight of galls, using these numbers down here. So 33, 28, 33, 37, 31, 32, 31, 28, 34, 28, 33, 26, 30, 31, and 28. It produces this normal probability plot down here. Now, mind you, the sample size for this is 15, which means we would need something that is better be pretty close to normal for us to be able to use this. But this normal probability plot down here looks to be pretty close, right? There's no underlying pattern, and they're pretty close to this line. I mean, again, there's some variability, of course, but it's pretty normal. So yes, this is going to be approximately normal. And as such, we could use this confidence interval. So it's approximately normal. And in order for us to do this, we need to calculate the margin of error, E. This would be that t value at alpha divided by 2. So we want the 95% confidence interval. We just found this in the last slide to be 2.145, but this would be t sub alpha divided by 2 times the sample standard deviation divided by the square root of the sample size. So just to put numbers to all these variables, this was 2.145 times sample standard deviation of 2.9 divided by square root of 15. Tossing this into a calculator, you get an answer of, and this is not rounded too much, as you could expect, but we have 1.606126 hectograms. So the margin of error, we need to take, I'll write it here, X bar plus and minus E. So 30.9 plus and minus 1.606126. So the lower bound, actually let me write out this. This would be 30.9 plus and minus 1.606126. The lower bound, when we subtract these two values, is going to give us a lower bound of 29.3 hectograms. And the upper bound, when we add them, is going to give us 32.5 hectograms. And the way that we could kind of interpret this confidence interval is that we are 95% confident. We are 95% confident that the limits of 29.3 hectograms and 32.5 hectograms actually do contain and let me just very quickly fix that O, which I just noticed did not come out as nice as I hoped. There we go. Which actually do contain the value of the population mean. The value of the population mean. And interpreting this confidence interval, which we just kind of did, but this is associating with a confidence level. When interpreting a confidence interval estimate of the mean mu, we want to know the confidence level gives us the success rate of the procedure used to construct the confidence interval. So again, this is in the form of 1 minus alpha. So whatever the confidence level is goes in this first underlined part, confidence level. So we are 1 minus alpha % confident that the interval from the lower bound to the upper bound actually does contain the true value of the mean mu. And again, we can interpret what that means. If we select many different samples, in the long run, 1 minus alpha % of the confidence intervals should contain the population mean. We could find a point estimate when having this confidence interval by taking the mean of the two bounds. So upper limit plus lower limit divided by 2. The margin of error takes the upper limit, subtracts the lower limit, and also divides by 2. And we could determine a sample size. But we first need a simple random sample. The sample size is calculated by rounding the following up to the next largest whole number as needed. N is equal to z sub alpha divided by 2 times the population standard deviation squared divided by the margin of error e. But we typically do not know the population standard deviation. We can use the range rule of thumb of the range divided by 4 for an estimate of the population standard deviation. We start the sample collection process and calculate the sample standard deviation S, though, in place of the population standard deviation sigma. This can be improved with more data, of course. Or we could estimate the population standard deviation by using the results of some other earlier study. So, for example, let's say we want to assume that the mean IQ score for the population of adults who smoke. How many smokers will be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? So from that last slide, we had this formula of z sub alpha divided by 2 times sigma divided by the margin of error, and we are squaring this entire value. So z sub alpha divided by 2 we have previously seen as 1.96 times the population standard deviation, which we are going to assume for this is equal to 15. Divided by the margin of error of 3 IQ points. So this uses the population standard deviation of 15. And we need to square this. If we toss this into a calculator, we get an answer of about 96.04. This rounds up to 97. So we need 97 people. 97 smokers. To estimate the population mean when the population standard deviation is known, very unlikely since we should know what the population mean is in that case, but that's besides the point. It's very unlikely to know that population standard deviation without knowing the population mean, but we can make the confidence interval as the margin of error with z sub alpha divided by 2 times the population standard deviation divided by the square root of n, the sample size. So for example, using the 15 birth weights of goals given in example 2, where the sample size is 15, the sample mean x bar is 30.9 hectograms, construct a 95% confidence interval estimate of the mean birth weight of all goals by assuming that the population standard deviation sigma is known to be 2.9. So for this, we are going to take margin of error we were just seen in the last slide is that z square sub alpha divided by 2 times sigma divided by the square root of n. So this would be 1.96 times 2.9 divided by the square root of 15. Toss that into a calculator, we should get an answer of about 1.46760. So we are going to take for this x bar plus and minus e. So x bar was 30.9. Adding and subtracting 1.46760. If we were to subtract those two, we would get an answer of 29.4 rounded hectograms. And the upper bound, when we add those two, we get an answer of 32.4 hectograms. So then we are 95% confident that the limits of 29.4 hectograms and 32.4 hectograms contains the mean birth weight of all goals, which would be then that population, to describe the population mean. Thank you.